So now we had this final equation of velocity profile. So this velocity profile equation can be further simplified if we use one concept and one assumption. The concept that we will be using is that the net mass flow rate in z direction per unit width will be zero. That is the this expression, that is integrating for any cross section from minus b to plus b, rho vz dy will be zero. This expression represents the net mass flow rate in z direction per unit width. As now we can see that the velocity here profile is that it goes in positive direction and then decreases and it becomes zero, and then it goes in negative direction. So this ensures that the net mass flow rate is zero over the cross section. Now we will substitute the density profile equation and temperature profile equation in this expression. So rho is equal to rho bar minus rho bar beta bar T minus T bar. In this expression, we know that rho bar is the average density and beta bar is the coefficient of volume expansion and T bar is the average temperature. And this temperature profile delta T is T2 minus T1. So we will be neglecting the delta T square terms, and after substituting these density and temperature profile equation back in this equation, we will get this equation. Now this equation, we have to integrate it from minus b to plus b, and this is the density profile equation in which temperature profile is substituted. Further, we will have to consider these three expression. Now p will be representing this term here, p will be representing this term, q will be representing this term, and r will be representing this term here. So if we substitute p, q, r for simplification, this integration will look like this. We will have integration from minus b to plus b, p into y cube by y by b whole cube minus y by b plus q into y by b whole square minus 1 rho bar plus r into y by b dy. So this will be the integration term. Now from minus b to plus b. And if we integrate these all equations, we will get this expression. Now in this expression, if we substitute values one by one, substituting values one by one, we will get this expression. Now in this also we have the limits minus b to plus b for all the terms, and we have PQR terms, and now we will discuss the PR term. Now what is P into R? Now P into R term is like P term value into R term value. So PR term. Now PR term here we have is like the value of P from this expression and the value of R from this expression. From here we can see that delta T is coming twice. So delta T into delta T will be T bar square. Sorry, delta T square. So delta T square, as we already know, delta T square will be close to zero or neglected. So PR term will be neglected. So if PR term is neglected or zero, this whole term will become zero. This whole term will become zero. And after substituting the limits, plus b and minus b in this expression, this term will become zero. This we can solve, and we can see that this term will become zero. So we have this term zero. Now we have this term also zero after substitution. And third, we will see that after substituting the limits, this term will be also zero. So these three terms will become zero, and we are left with only this term. So if we solve further, we can see that we are left with only this term. This term was zero, this term was zero, and this term was zero. So this term, if we put the limits, plus B and minus B. So Q into rho bar, this we will solve and we will come to this expression. After solving, we see that Q into rho bar minus 2B by 3 into, sorry, minus 2B by 3. This will become minus 4B by 3. So after simplifying, we can see that this becomes minus 4b by 3 into b square by 2 mu into dp by dz plus rho bar g. Now all these terms are constant and are sent to the right hand side, and we get this expression, which is our important result, that is dp by dz plus rho bar g is equal to 0. Now this, if this is 0, and if we substitute this result back in our velocity profile, this is our velocity profile, and we substitute this back here, so we will get the velocity profile equation as this, substituting dp by dz equal to minus rho bar g, this becomes 0. So velocity profile equation will be like this. It will be rho bar g beta bar delta t b square by 12 mu into y by v whole cube minus y by v. Now this is a simplified equation. Now also the second thing is that we can now calculate the average velocity. Now how we will calculate the velocity? If we calculate the average velocity between minus b to plus b, it will always come out to be 0. But we can calculate the average velocity for this region from here to here for positive region. So if we calculate the average velocity for positive region, if we use the average velocity formula there, so we see that the average velocity for upward moving stream, average velocity for this upward moving stream, that is it will be from minus b to 0. If we calculate the in this region, positive region, the average velocity comes out to be rho bar g beta bar delta t b square by 48 mu. So this will be the average velocity for this, and similarly for a negative direction the magnitude will be the same, and there will be minus vz somewhere here, the average velocity minus in that direction, negative direction. So now this velocity expression is converted into dimensional form. How we will convert this? We can write vz as p into vz rho bar by mu. Now this will convert the velocity into dimensional form, and y dash will be y by v. Now this will be replaced. So y by v, in place of y by v, we will write y dash, and in place of vz, we will convert it into form of vz dash. So this constant here, Grashof number. So this Grashof number comes out to be rho bar square g beta bar delta t into b cube by mu square. So this will be Grashof number. Now we will see the significance of Grashof number in the next slide.
So now we will be understanding the significance of Grashof number. So Grashof number can be written as this, where g is the acceleration due to gravity, beta is the coefficient of volume expansion or thermal expansion, delta t is a temperature difference, and v cube is the distance between two plates. Here we have given kinematic viscosity. So after that, if we substitute the value of kinematic viscosity as mu by rho, we will get the term of rho square over here. We'll get the rho square into g. Rho square into g is basically a measure of buoyancy force. Like what buoyancy is happening, above is the buoyancy term and below is the viscosity term. Above we can say it is buoyant force, and below is the viscous force or viscous dissipation. So this basically tells us the ratio of how much buoyancy is taking place compared to the viscosity. That is, it is relating the nature of the fluid and how much buoyancy, how far the fluid will rise, and it based on its viscosity. So now it is we will see the physical meaning. The Grashof number is a key dimensional number in fluid dynamics and heat transfer, and this is only there when we are dealing with natural convection or free convection. Like in Forced convection, the flow regime, we know the flow regime by Reynolds number. Here we know it by the Grashof number. And the physical meaning is buoyancy to viscous damping. Like if higher Grashof number is there, then more buoyant force is there. If more buoyant force is there, then we will have strong natural convection. Like in this case, we took only between flat plates. But if we have an open system, the buoyant force will be more and we will have strong natural concurrents. And again, Grashof number plays a role similar to Reynolds number in forced convection. Like here we can see the small Grashof number is there. It will be laminar flow and larger Grashof number, it could be turbulent also. Like we can take turbulent flow example like boiling is happen in a liquid. Then the bubbles violently move up, then it will be turbulent flow. Now, if we are analyzing air rising over a hot plate due to heating, the Grashof number tells it how vigorously the air will be circulated. That is the flow regime of the air, whether it is laminar, turbulent, or transient. In CFD modeling, also, Grashof number is a very important input to simulate free convection, buoyancy driven force between plates accurately. So again, flow regime, and here we will relate Grashof number to Prandtl number as we have talked in the first video. So lower Grashof number flow is smooth. Higher Grashof number flow becomes turbulent, leading to more mixing and higher heat transfer. And to compare the flow, to get a flow regime of, and to compare total regime, like total momentum diffusion, heat diffusion, and the flow. How is the flow happening? So this will basically tell us the flow regime, and this is the ratio of momentum and heat transfer. So combining these two equations, we will get both an account of heat transfer and momentum transfer along with the velocity profile. And from here, we could get the temperature profile. So again, critically, there's a certain value, and this might depend for different cases because again, in rate of moment, buoyant force and viscous force, the characteristic velocity and characteristic length could change. So that is what. Now we will see the application of free convection between flat plate in chemical engineering system basically. Now the problem we discussed its application we could see like how the problem could be useful. So main is cooling jacket and reactor. Well, usually the cooling jacket and reactor forced convection takes place, but in certain situations, like suppose shutdown is taking place or in passive mode, the fluid will be stagnant. So in that case, the heat transfer between reactor and wall often relies on free convection between the two vertical surfaces, that is the reactor wall and the jacket wall. And between these will be the fluid. So what happens is temperature control and reaction with this we can see. And one more important thing is suppose the pump is stopped, like some shutdown has happened, then we have to consider that the cooling jacket, it is conducting enough heat. So enough heat transfer is taking place even in the stagnant conditions so that overheating does not take place and it doesn't affect the reaction. And again in plate type heat exchangers. Plate type heat exchanger in passive mode, if the flow rate is low or stagnant in shutdown or passive safety modes. So heat transfer then occurs usually only by natural convection as one plate is hotter than another. And again in shutdown situations, we have to make sure that enough heat transfer is taking place. So the overheating does not happen. Now we will see for packed bed reactors. Packed bed reactors, what happens is there's usually a catalyst in the reactor and the flow through this fluid sometimes happen through natural convection, like where gases or liquids are not forced, but there's a temperature gradient due to exothermic reaction. And the free convection between these narrow plate-like spaces affects the heat distribution, affect the heat distribution of the uh, packed molecules, that is the catalyst. So in this case, we have to make sure that the proper heat transfer is taking place so that the catalyst does not get overheated and the catalyst does not get destroyed. So we have to make sure of that while designing the packed bed reactors. First, we had our problem statement here, and then we assumed assumptions. The main assumption is the length is greater than, the width between the plates is very small than the length of the plate. And T1 and T2, buoyancy force, the motion will happen. And yeah, these are also same assumptions. So we will assume velocity in only z direction. After assuming velocity in only z direction, we will get the combined flux equation. We use this combined flux equation to get the temperature profile. So first we got the temperature profile because the velocity depends on the temperature profile. After all, we use the shell balance equation, shell energy balance. We got this temperature profile from there. So this was our final temperature profile. So after this, we will find out the velocity profile. So we assume some certain velocity profile, and we use the equation of motion in Cartesian coordinates. We use the Navier-Stokes equation. We neglected two equations because velocity in only in z direction, and after that we neglected certain terms, and it became simplified. We only got three terms. Now rho we have to substitute. So we use Taylor series expansion over here to substitute the rho, and again we use the volume of coefficient of volume expansion term over here to calculate this. And after that, we got that how v is dependent on y, how v is a function of y. Here we got the v as a function of the length in y direction. So after that, we integrated this equation. We got a very complicated velocity profile. Now, in order to simplify this, we had one more assumption. We took that the total average, that is the net mass flow, that is the cross section flux in this direction will be zero. After this assumption, we took one more assumption that delta t square will be very small. And after that, we simplified this equation. We simplified this equation and got dp by dz is equal to minus rho g. And after getting this, we substituted and we got a simpler velocity profile. Next, what we did is we took the dimensionless things, dimensionless quantity of velocity and your length, and we got the Grashof number. And after that, we explain the significance of Grashof number, that is the ratio of buoyant force by viscous force.